When we first encounter physics, we are usually taught to think in terms of objects. There is a ball, a planet, an electron, a magnet. Each object seems to exist on its own, carrying properties like mass, charge, and position. Forces appear as simple pushes and pulls between these objects. This way of thinking feels natural because it matches human experience. We see objects, we touch objects, and we move objects. But Richard Feynman emphasized that this object-centered picture is incomplete and, at deeper levels, misleading. Physics does not fundamentally explain nature by focusing only on objects. Instead, it explains nature through fields that exist throughout space. To understand why this shift is so important, imagine trying to explain gravity using only objects. You have the Earth and the Moon. The Earth pulls the Moon, and the Moon pulls the Earth. But how does this pulling happen? There is no rope between them, no visible connection. If we say the Earth reaches out and pulls the Moon, we are not really explaining anything. We are just restating the mystery in different words. Feynman argued that physics advances when it replaces vague ideas with precise descriptions of what happens locally in space. This is exactly what fields do. A field assigns something to every point in space. For gravity, the gravitational field tells us, at each location, how strongly an object would be pulled, and in what direction if it were placed there. The Earth creates a gravitational field around it, spreading through space. The Moon moves the way it does because it is always responding to the gravitational field at its own location. There is no need for the Earth to know where the Moon is or to act across empty space instantaneously. The field already exists everywhere, quietly shaping motion. This idea removes the old notion of action at a distance, which troubled physicists for centuries. Action at a distance suggests that objects can affect each other instantly without anything happening in between. Feynman pointed out that this is deeply unsatisfying from a physical standpoint. Fields restore a sense of realism and continuity. Something real exists in space, and interactions happen step by step, point by point. Nature does not skip space, it fills it. Electricity provides an even clearer example. If you place an electric charge somewhere, it creates an electric field around it. Another charge introduced nearby feels a force, not because the first charge suddenly reaches out to it, but because it responds to the electric field already present at that location. If the first charge moves, the field changes, and that change travels through space at a finite speed. This means information and influence do not travel infinitely fast. They move through the field, respecting the structure of space and time. For Feynman, this was not just a technical detail, but a profound statement about how reality works. Thinking in terms of fields also changes how we understand empty space. In everyday language, empty space sounds like nothingness. But in physics, empty space can still contain fields. Even in a vacuum, gravitational and electromagnetic fields can exist, carrying energy and momentum. Light itself is an electromagnetic field oscillating through space. When sunlight travels from the sun to the Earth, it does not need a material medium. The field itself is the medium. This was a revolutionary idea when it first emerged, and Feynman stressed its importance because it forces us to abandon the idea that nothing means no physical content. Another key point Feynman made is that fields are not just convenient mathematical tools. They are as real as anything else in physics. You can measure the strength of an electric field at a point. You can calculate how much energy is stored in a magnetic field. You can observe how fields change and propagate. If energy flows from one place to another without matter moving between them, it is the field that carries that energy. This makes fields active participants in physical processes, not passive backgrounds. As physics developed further, especially with the rise of relativity and quantum theory, the central role of fields became even clearer. Einstein's theory of gravity does not describe gravity as a force between objects at all. Instead, it describes a gravitational field as the curvature of spacetime itself. Objects move the way they do because they follow paths determined by this curved field. In this view, Gravity is not something that acts on objects from outside. It is built into the structure of space and time. Feynman admired this shift because it showed how far the field concept could go in explaining nature more deeply and consistently. Quantum physics pushes the idea further still. In modern quantum field theory, particles are no longer treated as tiny solid points that exist independently. Instead, each type of particle corresponds to a field that exists everywhere. What we call a particle is a localized excitation, a small vibration in that field. An electron is not a little bead flying through space, it is a disturbance in the electron field. This means that fields are more fundamental than particles. Matter itself emerges from fields. Feynman often highlighted this idea because it overturns our everyday intuition and reveals a deeper layer of reality. This field-based view also unifies many different phenomena. Electricity and magnetism, once thought to be separate forces, are understood as different aspects of a single electromagnetic field. Changes in electric fields create magnetic fields, and changes in magnetic fields create electric fields. Light is simply a self-sustaining wave of these fields. From radio waves to X-rays, it is all the same underlying field behaving in different ways. Feynman saw this unification as one of the great successes of physics, made possible only by thinking in terms of fields rather than isolated forces between objects. Another important consequence of the field perspective is that it encourages us to think locally. Instead of asking how one object affects another far away, we ask what is happening at each point in space. What is the field here? How is it changing? How does matter respond to it? This local viewpoint is not only philosophically satisfying, but also essential for making accurate predictions. It aligns with the fundamental principle that no influence can travel faster than light. Fields change gradually, and their effects propagate through space in an orderly way. Feynman also emphasized that the field concept helps us accept uncertainty and probability, especially in quantum physics. Fields at the quantum level do not always have definite values. They fluctuate. They can exist in superpositions of possibilities. Yet these fluctuations are not arbitrary. They follow precise mathematical rules that allow physicists to calculate probabilities with extraordinary accuracy. By focusing on fields, physics finds a way to describe a world that is not rigidly deterministic yet still deeply lawful. Ultimately, when Feynman spoke about what physics means by fields, he was pointing to a shift in how we understand existence itself. The universe is not best described as a collection of solid objects floating in empty space. It is better described as a dynamic network of fields, continuously interacting, evolving, and shaping what we observe as matter in motion. Objects are patterns within fields, not the fundamental starting point. This first keynote captures a central lesson of modern physics. To understand nature, we must look beyond what our senses show us. Fields may be invisible, but they are not abstract fantasies. They are the underlying reality that connects forces, energy, space, and matter into a single coherent picture. By explaining nature through fields rather than just objects, physics reveals a universe that is far richer, more subtle, and more unified than everyday experience suggests. As this way of thinking settles in, it becomes clear that the shift from objects to fields is not just a technical improvement, but a change in worldview. Human intuition evolved to deal with solid things at human scales. We are comfortable imagining stones, trees, and tools, but deeply uncomfortable imagining invisible structures filling space. Feynman often pointed out that physics advances precisely when it goes beyond intuition. Fields are one of those ideas that initially feel abstract, yet they turn out to describe reality far more accurately than common sense ever could. One reason fields are so powerful is that they allow physics to describe continuity. Objects appear discrete and separate, but fields are smooth and extended. Between any 2 points in space, the field has a value, even if nothing material is present there. This continuity is crucial for understanding how changes happen. If a charge moves, the electric field around it does not rearrange itself instantaneously everywhere. The change spreads outward at a finite speed. This spreading is a physical process, not a mathematical trick. It is how nature enforces cause and effect. Feynman emphasized that fields give us a picture where the universe behaves responsibly, with influences traveling through space rather than jumping magically. The idea of fields also reshapes how we think about energy. In everyday thinking, energy belongs to objects. A moving car has kinetic energy. A lifted weight has potential energy. But in field-based physics, energy can belong to space itself. An electric field stores energy. A magnetic field stores energy. Even when no particles are present, energy can exist in the form of fields. This was a radical idea when it was first introduced, yet it is now essential to modern physics and technology. Every radio signal, every wireless transmission, every beam of light relies on energy carried by fields through empty space. Feynman found this especially beautiful because it unifies description and reality. Instead of saying energy is somehow hidden in relationships between objects, physics says energy is right there in space, measurable and real. If you could map the field everywhere, you could literally see where the energy is concentrated and how it flows. This idea leads directly to concepts like energy density and energy flux, which are central to understanding everything from electromagnetic waves to gravitational radiation. Another subtle but profound implication is that fields blur the line between what is material and what is not. Traditionally, matter was considered real and space was considered empty. Fields destroy that distinction. Space is no longer an empty stage where matter performs. Space itself has physical properties because it can host fields. This idea reaches its peak in modern theories, where spacetime itself behaves like a field, capable of stretching, bending, vibrating, and carrying energy. Feynman appreciated this because it showed how physics steadily strips away unnecessary assumptions and replaces them with simpler, more unified concepts. Fields also help explain why nature is so predictable despite its complexity. If interactions depended directly on every pair of objects, the universe would be impossibly complicated to describe. But because objects interact with local fields, the rules become manageable. Each object only needs to respond to the field at its own location. This locality makes it possible to write equations that govern behavior universally. The same field equations apply whether you are studying a laboratory experiment or the motion of galaxies. This is one of the reasons fields sit at the heart of physical law. Feynman also highlighted that fields are essential for understanding radiation. When an accelerating charge emits light, what is really happening is that it disturbs the electromagnetic field, creating ripples that travel outward. These ripples carry energy away from the charge. Without the field concept, radiation would be almost impossible to explain coherently. Fields provide a clear picture. Energy leaves the source, travels through space as a field disturbance, and is absorbed elsewhere. Nothing mysterious is required. At the quantum level, this picture becomes even richer. Fields are no longer smooth and quiet, they fluctuate. Even in their lowest energy state, quantum fields exhibit tiny vibrations. These fluctuations are not mere theoretical curiosities. They have measurable effects, such as forces arising from the structure of empty space itself. This means that what we casually call vacuum is actually a restless sea of fields in constant motion. Feynman loved pointing out such results because they force us to abandon naive ideas about emptiness and replace them with something far more interesting. Another important aspect of thinking in terms of fields is how it reframes causality. Instead of asking which object caused an effect, physics asks how the field evolved over time. Causes are encoded in how fields change and propagate. Effects arise because matter responds to those changes. This removes ambiguity and paradoxes that arise when we try to assign cause directly between distant objects. The field carries the cause forward through space and time in a precise, lawful way. Fields also provide a natural language for symmetry, one of the deepest ideas in physics. Many laws of nature are best understood as statements about how fields behave under transformations. Rotations, translations, and more abstract changes leave the fundamental equations unchanged. These symmetries are not decorative features, they determine what kinds of fields can exist and how they interact. Conservation laws, such as conservation of energy and momentum, emerge naturally from these symmetries. Feynman valued this connection because it shows that fields are not just descriptive tools, but are deeply tied to the logical structure of nature. As the field concept matured, it became clear that nearly all known forces can be described this way. Gravity, electromagnetism, and the nuclear forces all arise from fields. Each force corresponds to its own type of field, with its own properties and rules. The dream of physics has long been to unify these fields into a single framework. While that goal is not yet fully achieved, the progress made so far strongly suggests that fields are the right language for describing fundamental reality. Feynman's style was never to present fields as mystical or poetic ideas. He insisted that their value lies in their ability to predict experimental results. Fields earn their place in physics not because they sound elegant, but because they work. They allow physicists to calculate outcomes with astonishing accuracy. From the behavior of atoms to the signals from distant stars, field-based theories consistently match observation. This practical success is what ultimately justifies the abstract nature of the concept. By the time one fully absorbs this first keynote, it becomes impossible to return to a purely object-centered view of the universe. Objects still exist, but they are no longer the primary actors. They are participants in a deeper drama played out by fields filling space. Motion, force, energy, and even existence itself are mediated by these invisible structures. What Feynman wanted listeners to grasp was not just a definition, but a habit of thinking. When you see a phenomenon, do not immediately imagine objects reaching across space to affect one another. Instead, imagine the field quietly present everywhere, guiding how matter moves and how energy flows. This way of thinking is not only more accurate, but more powerful. It reveals a universe that is interconnected at every point, where space itself is alive with physical meaning. In this sense, physics explained through fields is not less real than everyday experience, but more so. It peels back the surface and shows the framework that holds everything together. Fields are the unseen architecture of reality, and understanding them is the first step toward understanding what physics truly means. To understand the second keynote, that fields describe how forces exist everywhere in space, we must let go of the deeply rooted idea that forces only appear when two objects interact directly. In ordinary thinking, a force feels like something that happens at a specific moment between specific things: a push, a pull, a collision. But physics reveals something far more subtle and far more powerful. Forces are not events that suddenly appear when objects come close. They are continuous features of space itself, present even when no object is there to feel them. This is the heart of the field concept as Richard Feynman emphasized it. Consider gravity. Even if there were no planets, no moons, no people standing on Earth, the gravitational field of the Earth would still exist. It fills the space around the planet in all directions. At every point in that space, the field has a specific strength and direction. The force we feel when we stand on the ground is simply our body responding to the gravitational field at that location. The force was already there before we arrived. We did not create it, we merely revealed it by being present. This idea immediately changes how we think about forces. A force is no longer something that one object does to another. It is something that space itself does to objects placed within it. The role of the source, like the earth in gravity or a charge in electricity, is to shape the field. Once shaped, the field exists independently and continuously. Any object that enters that region of space will experience a force because of the field, not because of a direct interaction with the source. Feynman stressed that this picture removes mystery rather than adding it. Instead of asking how the Earth reaches out to pull an apple downward, physics asks a simpler and more precise question. What is the gravitational field at the apple's position? Once that is known, the motion of the apple follows directly. The field acts locally. The apple responds only to what exists where it is. This locality is one of the most important principles in physics, and fields are the natural way to express it. Electric and magnetic forces make the omnipresence of fields even clearer. Place an electric charge somewhere in space, and the electric field immediately exists everywhere around it. You can draw imaginary lines to represent this field, but those lines correspond to something real. At each point in space, the field tells you what force a test charge would feel if placed there. You do not need a second charge present for the field to exist. The field is a property of space caused by the presence of the source charge. This means that space is not passive. It is structured. It carries information about forces. When Feynman spoke about this, he wanted listeners to understand that fields are not forces themselves, but carriers of force. They encode how forces would act if matter were present. This distinction matters because it allows physics to describe situations consistently even when objects are moving, appearing, or disappearing. The idea that forces exist everywhere through fields also explains why changes in forces take time to propagate. If a charge suddenly moves, the electric field near it changes first. That change then spreads outward at the speed of light. Distant regions of space do not instantly know that the charge has moved. They only respond once the field disturbance reaches them. This behavior is impossible to explain using a simple object-to-object force model, but it emerges naturally when forces are understood as field phenomena. Feynman often emphasized that this spreading of field changes is not just a mathematical convenience. It is a physical process. The field itself evolves over time. It can store energy, release energy, and transport energy from one place to another. When a radio antenna transmits a signal, it is not throwing particles across space in a straight line. It is disturbing the electromagnetic field, creating waves that move outward and carry energy and information. Every point in space along the way plays a role in this transmission. Another important implication is that forces do not need targets to exist. A magnetic field around a magnet exists even if there is no iron nearby. The moment you bring iron into that region, the force becomes visible as motion. But the field was already there, silently shaping the possibilities. Feynman liked this way of thinking because it separates cause from effect in a clean and logical way. The source causes the field. The field causes the force on objects. Each step is local and well-defined. This view also helps explain why different forces can overlap in the same region of space without interfering with each other. At a single point, there may be a gravitational field, an electric field, a magnetic field, and even more exotic fields all coexisting. An object placed there responds according to its properties. A neutral object responds to gravity, but not to electricity. A charged object responds to both. Space itself contains all the fields simultaneously, and matter selects which ones matter to it. This selective response would be extremely difficult to describe without the field concept. Feynman pointed out that fields give physics a kind of universality. Once the field is known everywhere, the behavior of any object can be predicted. You do not need a separate rule for every pair of interacting objects. You only need the field and the laws that describe how objects respond to it. This drastically simplifies our understanding of nature. Instead of a tangled web of direct interactions, we have a structured environment where forces are built into space. The omnipresence of fields also reshapes our understanding of stability and equilibrium. Objects can rest in stable positions because of the structure of the field around them. A marble resting at the bottom of a bowl is responding to a gravitational field shaped by the bowl's surface. Similarly, electrons remain bound to atoms because of the electric field created by the nucleus. These are not arbitrary arrangements. They are consequences of field configurations that minimize energy. At a deeper level, this way of thinking leads naturally to the idea that the laws of physics are field laws. Equations like those governing electromagnetism do not describe forces between specific charges. They describe how fields behave everywhere in space and time. From those field equations, Forces emerge automatically when matter is introduced. Feynman emphasized that this reversal, fields first, forces second, is one of the great conceptual achievements of physics. Another profound consequence is that fields make it possible to talk meaningfully about forces in empty space. Gravitational waves, for example, are ripples in the gravitational field that travel through the universe, even where no matter is present. They carry energy and momentum purely through changes in the field itself. The fact that such waves can exist and be detected confirms that fields are not just bookkeeping devices. They are physical entities capable of independent existence. Feynman also liked to stress that thinking in terms of fields helps avoid philosophical confusion. If forces existed only when objects interacted, it would be hard to explain potential effects and stored energy. Fields solve this by making the potential real. The energy stored in a stretched spring or a charged capacitor is actually energy stored in the field configuration. Space itself holds that energy until it is released. As one becomes comfortable with this idea, it becomes clear that fields give physics its predictive power. Knowing how fields are distributed allows physicists to foresee motion, radiation, and interaction long before anything dramatic happens. Fields encode the future possibilities of force. They are like a map of influence spread across space. By insisting that forces exist everywhere through fields, Feynman was guiding listeners toward a deeper realism. The world is not a collection of isolated interactions popping into existence when objects meet. It is a continuous, structured environment where forces are woven into space itself. Objects move the way they do because they are immersed in this environment at every moment. This second keynote reveals that fields are not optional explanations layered on top of forces. They are the very way forces exist in nature. Space is active, informative, and powerful. To understand forces is to understand fields, and to understand fields is to recognize that every point in space carries physical meaning, even when it appears empty. As this understanding deepens, it becomes clear that describing forces as fields everywhere in space also changes how we think about time. Forces are no longer instantaneous commands issued by one object to another. They are ongoing conditions of space that evolve. When something changes, the change does not leap across the universe, it travels through the field. This gives time a physical role in interactions. The universe responds gradually, not abruptly, and this gradual response is built into the structure of fields themselves. Feynman often used simple language to explain that a field at a point contains instructions for motion. If an object is placed there, the field tells it how to accelerate, but these instructions are not static. They can change as the sources change, and those changes propagate outward. This makes the universe feel less like a collection of isolated events and more like a continuous process, unfolding everywhere at once. Every region of space participates in the dynamics, whether or not matter is present. This viewpoint also helps us understand why forces can appear smooth and predictable even when the sources are complex. A planet may be made of countless particles, yet its gravitational field far away is simple and stable. The field averages over the details of the source and presents a clean, coherent influence to distant space. Feynman admired this because it shows how nature hides complexity behind elegant structures. Fields act as a bridge between messy microscopic details and orderly large-scale behavior. Another important insight is that fields allow forces to be superposed. If two sources create fields in the same region, the total field is simply the combination of both. This means space can carry multiple influences at once. An object placed there feels the combined effect. This superposition principle is not just mathematically convenient, it reflects a deep property of how fields behave. Without it, predicting motion in complex environments would be nearly impossible. Feynman emphasized that superposition makes fields incredibly powerful explanatory tools. You do not need to trace every individual interaction. You only need to know how fields add together. Whether studying electric circuits, planetary motion, or waves in space, the same idea applies. Forces blend smoothly through fields rather than colliding awkwardly like physical objects. The field perspective also clarifies why forces can be shielded or blocked in some cases but not others. Electric fields can be cancelled inside conductors because charges rearrange themselves to reshape the field. Gravitational fields, however, cannot be shielded in the same way. This difference is not mysterious once forces are understood as fields with different properties. Each type of field follows its own rules about how it spreads, how it interacts with matter, and how it can be modified. As physics progressed, the realization that forces are field effects everywhere in space led to remarkable technological advances. Power generation, wireless communication, medical imaging, and countless other technologies rely on controlling and manipulating fields rather than objects. Engineers do not design devices by imagining forces jumping between components. They design field configurations that guide energy and information where they want it to go. Feynman often delighted in pointing out that abstract ideas like fields become intensely practical once we truly understand them. At the cosmic scale, this same concept explains the large-scale structure of the universe. Galaxies move as they do because of gravitational fields extending across enormous distances. Light bends near massive objects because it travels through regions where the gravitational field alters the structure of space and time. These are not special cases, they are natural consequences of forces existing everywhere through fields. At the smallest scales, fields are just as essential. Inside atoms, electric fields determine how electrons arrange themselves. Inside atomic nuclei, more powerful fields bind protons and neutrons together. These forces do not suddenly turn on when particles get close. They are always present, shaping possibilities even before interactions occur. Feynman stressed that this continuous presence is what makes stable structures possible at all. Another subtle but important point is that fields make forces objective. They exist whether or not anyone measures them. A gravitational field does not appear because we calculate it. It exists because mass shapes space. Measurements simply reveal what is already there. This realism appealed strongly to Feynman, who valued physical explanations that did not depend on human observation for their existence. Fields also help resolve paradoxes that arise when thinking only in terms of forces between objects. For example, questions about where energy is during interactions become clearer. If a force acts at a distance, it is unclear where the energy resides. With fields, the answer is straightforward: energy is stored and transported by the field. When a force does work, energy flows through space via the field. This provides a consistent accounting that works in all situations. As this way of thinking becomes natural, one begins to see space differently. It is no longer an empty backdrop, it is an active participant in physical processes. Every point in space holds information about forces, waiting to influence matter that passes through. Fields turn space into a dynamic environment rather than a passive void. Feynman wanted learners to internalize this shift because it changes how questions are asked. Instead of asking, which object is pulling which, physics asks, what is the field here, and how is it changing? This shift leads to clearer reasoning, fewer contradictions, and deeper insight. It aligns with how nature actually behaves rather than how it appears at first glance. In the end, the idea that forces exist everywhere through fields reveals a universe that is continuously connected. Nothing is truly isolated. Even in apparent emptiness, forces are present as fields shaping future motion and possibility. Objects move, interact, and evolve not because of sudden, mysterious pulls, but because they are immersed in a structured sea of fields that fills all of space. This is one of the most profound lessons physics offers, and one that Richard Feynman believed was essential to understanding the true meaning of physical law. To grasp the third keynote, that particles respond to fields rather than direct contact, we must carefully separate everyday intuition from the deeper logic of physics. In daily life, motion usually follows touch. A hand pushes a box, a foot kicks a ball, a hammer strikes a nail. Cause and effect seem inseparable from physical contact. But as Richard Feynman emphasized, this intuition breaks down completely when we examine the fundamental workings of nature. At the most basic level, particles do not wait for contact to respond. They move, accelerate, and change direction because of the fields present where they are. Imagine a single electron floating in space. Nothing touches it. There is no surface, no medium, no mechanical connection. Yet, if an electric field exists at the electron's location, it accelerates. Something real has happened, even though nothing touched it. The cause of that motion is not another particle making contact, but the local value of the field. Feynman insisted that this is not a poetic metaphor, it is a precise physical statement. The electron responds to the field at its position, and that response fully explains its behavior. This local response is crucial. The electron does not need to know where the field came from. It does not need to know whether the field was created by a nearby charge, a distant star, or a changing magnetic environment. All that matters is the field here and now. This principle, that particles respond only to local fields, is one of the deepest organizing ideas in physics. It ensures consistency, predictability, and causality. Gravity offers a familiar but profound example. A falling apple is not pulled directly by the earth in the sense of a physical grip. The apple simply follows the gravitational field at its location. If the earth were suddenly to change its mass distribution, the gravitational field near the apple would change only after a delay, and the apple's motion would respond only after that change arrived. This shows that the apple does not respond to the earth as an object, but to the gravitational field as a physical condition of space. Feynman often highlighted this point because it removes confusion about how interactions happen. There is no need to imagine invisible strings or instant communication. The field is already present, and the particle reacts to it according to simple, universal rules. Once the field is specified, the motion of the particle follows inevitably. Electric and magnetic interactions reinforce this idea even more strongly. A charged particle placed in an electric field accelerates immediately. Even if the source of the field is far away, the source does not act directly on the particle. The field does. Similarly, a moving charged particle responds to a magnetic field by curving its path, even though the magnetic field exerts no force along the direction of motion. This strange behavior makes sense only when we accept that the field itself is the agent of influence. Feynman emphasized that particles are not passive objects being pushed around. They are dynamic entities with properties that determine how they respond to fields. Mass determines how a particle responds to gravitational fields. Electric charge determines how it responds to electric and magnetic fields. Spin and other quantum properties determine responses to more subtle fields. Fields provide the environment, and particles respond according to their nature. This perspective also clarifies why different particles behave differently in the same region of space. In a given location, the gravitational field, electric field, and magnetic field may all exist simultaneously. A neutral particle responds only to gravity. A charged particle responds to gravity and electromagnetism. A photon responds to the structure of spacetime itself. The difference is not in the fields, but in the particle's ability to respond to them. This selective responsiveness is a fundamental principle that becomes clear only when fields, not contact, are seen as primary. At the microscopic scale, contact itself loses meaning. When two particles appear to collide, what actually happens is a complex exchange of field interactions. Electric fields repel electrons before they ever touch. Atomic nuclei never make physical contact in the classical sense. Their interactions are mediated by fields. What we perceive as solidity is actually the result of field-based repulsion. Feynman loved pointing out that nothing truly touches anything else in the way our senses suggest. Matter resists matter because of fields, not because of hard surfaces colliding. This realization reshapes our understanding of material reality. A table feels solid not because its atoms are packed together like tiny billiard balls, but because the electromagnetic fields associated with its atoms strongly resist compression. Your hand responds to those fields by stopping. The sensation of touch is actually a response to fields. Direct contact, in the everyday sense, is an illusion created by field interactions. Feynman also stressed that thinking in terms of particle response to fields allows physics to remain consistent with relativity. If particles responded directly to distant objects, interactions could be instantaneous, violating the speed limit set by the speed of light. Fields prevent this. Changes in fields propagate at finite speeds. Particles respond only when the field change reaches them. This preserves causality and ensures that effects follow causes in the correct order. Another powerful consequence of this idea is that it allows physics to describe complex systems using simple rules. Instead of tracking every interaction between every pair of particles, physics describes how fields evolve and how particles respond locally. This dramatically reduces complexity. Each particle needs only to read the field at its own position. The rest of the universe influences it indirectly through the field. At the quantum level, this idea becomes even more striking. Particles are not little points following definite paths. Their behavior is described by probability amplitudes, which themselves are field-like objects. The response of a particle to a field is governed by quantum rules that allow for uncertainty, superposition, and interference. Yet even here, the core idea remains the particle responds to the field configuration at its location, not to distant objects directly. Feynman emphasized that this way of thinking does not make reality vague or mystical. On the contrary, it makes it more precise. The rules governing particle response to fields are among the most accurately tested laws in all of science. Predictions based on these rules match experiments to extraordinary precision. This success is not accidental. It reflects the fact that fields capture how nature actually operates. As one reflects on this, it becomes clear that the third keynote is not just a statement about forces. It is a statement about how information flows in the universe. Particles do not need global knowledge. They do not calculate what distant objects are doing. They simply respond to the local field. This local response, multiplied across countless particles and points in space, produces the rich and complex behavior we observe. In this view, the universe becomes a vast system of local interactions guided by fields. Order emerges not from direct coordination between distant objects, but from consistent local responses to shared fields. This is a deeply satisfying picture because it explains complexity without invoking hidden connections or mysterious influences. By understanding that particles respond to fields rather than direct contact, we begin to see matter not as isolated chunks colliding in empty space, but as active participants in a field-filled environment. Every motion, every force, every interaction becomes a dialogue between particles and the fields they inhabit. This idea, central to Feynman's thinking, reveals a universe that is coherent, local, and profoundly interconnected at every point. As this idea settles in, it becomes clear that particle response to fields also explains why motion often appears smooth and continuous, even though matter is made of discrete particles. Fields vary smoothly across space, and particles continuously adjust their motion as they move through these variations. There are no sudden jumps caused by invisible collisions at a distance. Instead, there is a steady dialogue between particle and field, unfolding moment by moment. Feynman valued this picture because it replaces mystery with clarity. This perspective also reshapes how we think about force itself. Force is not an external shove imposed on a particle. It is the result of how a particle's properties couple to the surrounding field. The same field can exist at a point, but different particles respond differently. A particle with greater mass resists acceleration in a gravitational field more strongly. A particle with higher electric charge responds more dramatically to an electric field. Force, then, is not something universal that happens to everything equally. It is a relationship between a particle and a field. Feynman often emphasized that this relationship is governed by simple rules. Once those rules are known, the behavior of particles becomes predictable. There is no need to imagine complicated mechanisms behind the scenes. The field provides the influence, and the particle responds according to its nature. This elegance is one of the reasons field-based physics is so powerful. Another important implication is that particles do not carry forces with them. A charged particle does not drag an electric force around like a personal attribute. Instead, it modifies the field around it. Other particles respond to that field when they enter it. This separation of roles, sources shape fields, particles respond to fields, keeps physics logically clean. Feynman stressed that confusion often arises when people mix these roles together. This distinction also helps explain why interactions can be delayed or altered by changes in the environment. If a charged particle moves behind a shield, the field in a certain region may change, and particles there will respond differently. Nothing about the particles themselves has changed, only the field they experience has. This again highlights that particles respond to conditions of space, not to distant objects directly. At very high energies or very small scales, the idea of particle response to fields becomes even more essential. In particle accelerators, scientists do not hurl particles at each other hoping for contact. They manipulate electric and magnetic fields to guide, accelerate, and focus particles. The entire process relies on predictable particle responses to carefully designed field configurations. Feynman loved using such examples because they show how abstract ideas translate directly into practical control. Quantum theory deepens this picture rather than replacing it. In quantum physics, particles interact by exchanging quanta of fields. What looks like a force between particles is actually a field-mediated process. Even then, the interaction remains local. The particle interacts with the field at its position. There is no sudden leap across space. This preserves the core principle that particles respond to fields, not to each other directly. This view also clarifies why empty space can influence particles. Even in regions without obvious sources, background fields can exist. A particle passing through such a region may experience effects that have no classical explanation in terms of contact. These effects make sense once fields are accepted as real physical entities filling space. Feynman often pointed out that the universe is far more active than it appears, even where nothing seems to be happening. Another subtle insight is that particle identity itself is tied to field response. What makes an electron is not just its mass or charge, but how it responds to various fields. Its behavior in electric, magnetic, and gravitational fields defines its role in nature. In this sense, particles are characterized by their patterns of response. Fields provide the context in which these patterns are expressed. As this way of thinking becomes natural, the idea of direct contact fades in importance. What we call contact is simply the result of extremely strong field responses occurring over very small distances. There is no fundamental boundary where fields stop and objects begin. Everything blends smoothly into field interactions. Feynman believed that accepting this view helps prevent common misunderstandings in physics. Many paradoxes arise from imagining particles as tiny solid objects colliding in empty space. When we instead see them as entities responding continuously to fields, those paradoxes dissolve. Motion, force, and interaction become aspects of a single coherent framework. In the end, the third keynote reveals a universe governed by local responses rather than distant commands. Particles do not reach out to one another. They listen to the fields around them and act accordingly. This simple rule, applied everywhere and at all times, generates the immense complexity of the physical world. By embracing the idea that particles respond to fields rather than direct contact, we gain a clearer, more faithful picture of reality. It is a picture in which space is active, interactions are local, and nature operates through elegant, consistent principles. This was the clarity Feynman sought, and it remains one of the most profound insights physics has to offer. For much of human history, the idea that one object could influence another without touching it felt deeply unsettling. Early explanations of gravity, magnetism, and electricity often relied on the vague notion that objects somehow acted across empty space. This idea, known as action at a distance, worked well enough for calculations, but left a serious conceptual problem. How could something here affect something there, with nothing in between? Richard Feynman emphasized that modern physics does not accept this mystery as fundamental. Instead, it replaces action at a distance with fields, and in doing so restores a clear and physically meaningful picture of how interactions actually occur. Action at a distance suggests that space itself plays no role in physical processes. Objects simply reach across emptiness and influence one another instantly. This view troubled even the greatest scientists. It leaves unanswered questions about how influence travels, where energy resides during interaction, and how cause and effect are maintained. Feynman pointed out that such questions are not philosophical distractions, they are signs that a theory is incomplete. Physics seeks mechanisms that operate locally, step by step through space and time. Fields provide exactly this mechanism. Instead of saying that one object directly affects another far away, physics says that objects create fields around them. These fields exist everywhere in space and carry the influence outward. Another object is affected only when it encounters the field at its own location. Nothing jumps across space. Something real fills that space and mediates the interaction. This replacement is not cosmetic, it fundamentally changes how we understand causality. Consider gravity once more. In an action at a distance picture, the Earth pulls the Moon instantly, no matter how far away it is. In a field-based picture, the Earth shapes the gravitational field around it. That field extends through space, and the Moon moves because it is embedded in that field. If the Earth were somehow altered, the change in the gravitational field would propagate outward at a finite speed. The Moon would respond only after that change arrived. Cause and effect are preserved naturally. Feynman stressed that this idea removes the need for hidden connections or instantaneous signals. Fields make interactions local. At every moment, an object responds only to what exists where it is. The rest of the universe influences it indirectly through the structure of the field. This locality is not just aesthetically pleasing. It is required by relativity, which forbids faster than light influence. Fields and relativity fit together seamlessly, while action at a distance does not. Electric and magnetic phenomena show this replacement even more clearly. When a charge moves, the electromagnetic field around it changes. That change travels outward as a wave. Another charge responds when the wave reaches it, not before. There is no mysterious leap. The field carries both energy and information through space. Experiments confirm this behavior with extraordinary precision, leaving no room for instantaneous action at a distance. Another advantage of replacing action at a distance with fields is clarity about energy. In older views, it was unclear where energy was during an interaction. If two objects attract each other across space, where is the energy stored before they move? Fields answer this cleanly. Energy is stored in the field configuration itself. As objects move, energy flows through space via the field. Nothing appears or disappears without explanation. The accounting becomes consistent and complete. Feynman also emphasized that fields allow interactions to be visualized and analyzed dynamically. One can study how a field changes over time, how it propagates, how it interacts with matter, and how it carries momentum. This dynamic picture is impossible with action at a distance, which treats interactions as static relationships rather than evolving processes. At a deeper level, replacing action at a distance with fields transforms our view of space. Space is no longer an empty void separating objects. It becomes an active participant in physical reality. It can store energy, transmit influence, and shape motion. This idea may feel abstract, but it has real consequences. Technologies such as radio communication, radar, and modern electronics all rely on manipulating fields, not on exploiting action at a distance. Feynman believed that one of the great achievements of physics was eliminating unnecessary mystery. Action at a distance was mysterious because it offered no mechanism. Fields, while initially abstract, provide a concrete structure that can be tested, measured, and understood. They do not merely describe interactions, they explain how interactions occur. By replacing action at a distance with fields, physics achieves a deeper honesty about nature. It acknowledges that influences must travel through space and time, that energy must reside somewhere, and that causes must precede effects in a continuous way. This shift does not make the universe simpler in appearance, but it makes it far more coherent. In this sense, the field concept is not just a technical improvement, but a conceptual liberation. It frees physics from vague explanations and anchors interactions in something real and local. What once seemed like mysterious attraction across emptiness becomes a clear story of fields filling space, evolving and guiding motion. This is the clarity Richard Feynman championed, and it remains central to how physics understands the universe today. One of the most profound shifts introduced by the field concept is the realization that energy and momentum do not belong only to objects. In everyday thinking, energy seems inseparable from matter. A moving car has energy, a raised object has energy, a heated object contains energy. This way of thinking feels natural because it matches direct experience. But Richard Feynman emphasized that physics reveals a deeper truth. Energy and momentum can exist in fields themselves, even in regions of space where no matter is present. This idea initially feels strange because fields are invisible. We are accustomed to associating energy with things we can see or touch, yet experiments and theory both show that fields can store energy in a precise, measurable way. An electric field between two charged plates contains energy. A magnetic field around a current-carrying wire contains energy. If the field configuration changes, that energy can be released, transferred, or transformed into other forms. Nothing material needs to move for this to happen. Space itself, through the field, carries physical substance. Feynman often pointed out that this realization solves old puzzles about where energy goes during interactions. Consider two charged objects attracting each other. Before they move, energy is already present in the electric field between them. As they come closer, the field changes, and energy flows from the field into the motion of the particles. There is no mysterious creation of energy at the moment of motion. It was already there, distributed in space. The same is true for momentum. When light strikes an object, it can push it, even though light has no rest mass. This would be impossible if momentum belonged only to matter. But light is an electromagnetic field, and that field carries momentum. When the light is absorbed or reflected, momentum is transferred from the field to the object. This transfer has been measured countless times and is essential to technologies such as solar sails and radiation pressure systems. Fields do not just influence motion, they actively participate in it. Feynman emphasized that once energy and momentum are recognized as properties of fields, many confusing situations become clear. For example, when a radio antenna emits a signal, energy leaves the antenna and travels through space. Where is that energy? It is not riding on particles like a package on a truck. It is carried by oscillations in the electromagnetic field. Every point in space the wave passes through temporarily holds energy and momentum as the field vibrates. Space becomes a conduit, not an emptiness. This understanding also reveals why fields are dynamic rather than static. A field is not just a background influence, it is a system capable of motion and change. Energy stored in a field can flow, spread, concentrate, or disperse. The equations of physics describe not only how fields affect matter, but how fields themselves evolve. Feynman appreciated this because it gave fields a kind of physical independence. They are not shadows of matter, they are actors in their own right. Another important consequence is that conservation laws take on a deeper meaning. Conservation of energy and conservation of momentum apply not just to particles but to fields as well. When energy seems to disappear from matter, it often reappears in a field. When momentum changes in an object, the field balances the change. This ensures that physical laws remain consistent even in complex interactions involving radiation and waves. Feynman also liked to point out that the idea of energy in fields explains why disturbances can travel through empty space. A wave is simply a moving pattern of energy and momentum in a field. Water waves move energy through water, sound waves move energy through air, and electromagnetic waves move energy through empty space. The last case seems impossible unless we accept that the field itself carries energy. Once that is accepted, light traveling through a vacuum becomes perfectly natural. At a deeper level, recognizing energy in fields blurs the line between matter and space. If space can store energy and momentum, then it has physical properties. This idea reaches its peak in modern theories, where the energy of fields can influence the structure of space itself. Feynman did not claim that these ideas were fully understood, but he emphasized that the direction was clear. Fields are fundamental carriers of physical reality. This keynote also changes how we think about interactions at a distance. Energy does not jump from one object to another, it flows through the field connecting them. Momentum does not vanish and reappear elsewhere. It is transferred locally through field interactions. This local flow preserves causality and makes the universe intelligible. By understanding that energy and momentum live inside fields, we gain a more complete and honest picture of nature. Fields are no longer abstract mathematical conveniences. They are repositories of energy, conveyors of motion, and essential components of every physical process. This insight, strongly emphasized by Richard Feynman, reveals that the fabric of the universe is not made only of matter, but of energetic fields filling all of space. Modern physics stands on the foundation of the field concept. Without it, the theories that successfully describe nature at its deepest levels would collapse into disconnected pieces. Richard Feynman often stressed that fields are not optional additions to physics. They are the language in which the laws of nature are written. From classical electromagnetism to quantum theory and relativity, fields provide the structure that unifies explanation, prediction, and observation. One of the clearest demonstrations of this is electromagnetism. Electric and magnetic effects were once treated as separate phenomena, each with its own rules. The introduction of the electromagnetic field unified them into a single framework. Electric fields and magnetic fields are not independent entities, but different aspects of the same underlying field. Changes in one produce changes in the other. Light itself emerges naturally as a wave of this field. This unification would be impossible without the field concept, and it became a model for how physics seeks deeper understanding. Einstein's theory of gravity extends this idea even further. Gravity is no longer described as a force acting between masses. Instead, it is described as the geometry of spacetime itself. Massive objects shape the gravitational field by curving spacetime, and other objects move along paths determined by that curvature. In this view, the field is not something placed in space, it is the structure of space. Feynman admired this leap because it showed how the field concept could absorb what once seemed like separate ideas, force, space, and motion to a single coherent picture. Quantum physics also depends fundamentally on fields. Early quantum theories tried to treat particles as primary, with fields playing a secondary role. This approach quickly reached its limits. Modern quantum theory recognizes that each type of particle corresponds to a field that exists everywhere. Particles appear as excitations of these fields, like ripples on the surface of a vast ocean. This shift resolves many inconsistencies and allows calculations that match experiments with astonishing accuracy. Feynman was deeply involved in developing and explaining quantum field theory, and he emphasized its success as evidence that fields are fundamental. Predictions made using this framework have been confirmed to extraordinary precision. Such success is not accidental. It reflects the fact that fields capture how nature actually operates, even when that operation defies everyday intuition. Another reason modern physics relies on fields is their compatibility with fundamental symmetries. Many of the most important principles in physics, such as conservation of energy, momentum, and charge, are naturally expressed in terms of fields. These conservation laws arise from symmetries in how fields behave under changes of time, space, and orientation. This deep connection between symmetry and physical law becomes clear only when fields are placed at the center of theory. Fields also provide a natural framework for unification. Physics seeks to describe diverse phenomena using a small number of underlying principles. Field theories allow different forces and particles to be described using similar mathematical structures. This has led to partial unifications that explain a wide range of observations with remarkable economy. While a complete unification remains an open challenge, the field-based approach continues to guide progress. Feynman often reminded audiences that the power of fields lies not only in their explanatory reach, but in their predictive strength. Field equations allow physicists to calculate outcomes before experiments are performed. These predictions guide the design of experiments and technologies. From particle accelerators to satellites, modern science and engineering depend on accurate field-based models. Another important aspect is that fields bridge scales. The same basic concepts apply whether one is studying subatomic particles or cosmic structures. This continuity is rare and valuable. It suggests that physics is not a patchwork of unrelated rules, but a unified description of reality across all scales. Fields provide the common thread. By building modern physics on fields, scientists have achieved a level of understanding that would be impossible otherwise. Fields connect forces, particles, space, and time into a single framework. They transform our view of the universe from a collection of interacting objects into a dynamic, interconnected system governed by elegant laws. This keynote reflects Feynman's belief that the true strength of physics lies in the concepts that endure across theories. Fields are one of those concepts. They are not temporary models waiting to be replaced. They are the foundation upon which our best understanding of nature is built, and they continue to shape the future of physics. Modern physics does not merely use fields as a convenient tool, it depends on them at every level. As scientific understanding deepened, physicists discovered that trying to explain nature without fields led to contradictions, gaps, and unanswered questions. Richard Feynman repeatedly emphasized that once fields are removed, the entire structure of modern physics collapses. Fields are not an optional layer added on top of particles and forces. They are the foundation upon which the laws of nature are written. One of the clearest reasons for this is the need for consistency across space and time. Physics seeks laws that apply everywhere, not just in special situations. Fields provide exactly this universality. They exist at every point in space and evolve continuously in time according to precise rules. These rules do not depend on where an experiment is performed or who observes it. This universality is what gives physics its power to predict phenomena ranging from atomic behavior to the motion of galaxies. Electromagnetism offers a striking example of how deeply physics relies on fields. Electric and magnetic effects cannot be fully understood as separate forces acting between objects. They emerge from a single electromagnetic field that fills space. Changing electric fields generate magnetic fields, and changing magnetic fields generate electric fields. Light itself is nothing more than a traveling disturbance in this field. Without the field concept, these connections would appear accidental. With fields, they become inevitable. Gravity shows an even more dramatic dependence on fields. In modern physics, gravity is not treated as a force in the traditional sense. Instead, it is understood as a gravitational field that shapes the geometry of space and time. Objects move the way they do because they follow paths determined by this field. This description removes the need for gravitational forces acting at a distance and replaces it with a field-based structure that governs motion everywhere. Feynman admired this approach because it demonstrates how fields can replace older, less coherent ideas with a unified framework. Quantum physics makes fields unavoidable. Early attempts to describe quantum behavior using particles alone quickly failed. The behavior of particles could not be explained without invoking fields that permeate space. Modern quantum theory recognizes that every fundamental particle corresponds to a field that exists everywhere. What we observe as particles are localized excitations of these fields. This realization transformed physics, revealing that fields are more fundamental than matter itself. Feynman was deeply involved in the development of quantum field theory and often pointed to its extraordinary success. Calculations based on this framework match experimental results with unmatched precision. Such accuracy is not achieved by chance. It reflects the fact that quantum field theory captures the true structure of physical interactions. Fields provide the stage, the rules, and the dynamics through which all processes unfold. Another reason modern physics depends on fields is their connection to symmetry. The most fundamental laws of physics are expressions of symmetry, and these symmetries are naturally described in field language. Conservation of energy, momentum, and charge arise because the underlying fields behave the same way under shifts in time and space. Fields make these deep relationships transparent, while object-based descriptions hide them. Fields also allow physics to scale smoothly from the smallest to the largest systems. The same conceptual framework explains the interactions inside an atom and the behavior of stars and galaxies. This continuity is one of the strongest indications that fields reflect something fundamental about reality. Physics does not need separate rulebooks for different scales when fields are used as the foundation. Feynman emphasized that the strength of a scientific concept lies in how long it survives. Fields have survived every major revolution in physics. Each new theory has not discarded them but deepened their meaning. Classical fields led to relativistic fields, which led to quantum fields. At every stage, the field concept became more central, not less. By recognizing that modern physics is built on fields, we gain insight into why the universe is understandable at all. Fields provide order, continuity, and structure. They allow nature to be governed by simple principles that operate everywhere. This is why fields are not merely a chapter in physics. They are its backbone, shaping how reality is described and understood. At the deepest level, the concept of fields reveals a powerful connection between matter, space, and reality itself. What once appeared as separate ingredients of the universe, solid objects, empty space, and invisible forces, are now understood as aspects of a single, interconnected structure. Richard Feynman emphasized that fields are the bridge that unites these elements into one coherent picture of nature. Matter, in the modern view, is no longer the fundamental starting point. Particles are not isolated building blocks floating in emptiness. Instead, they are expressions of underlying fields that fill all of space. An electron exists because the electron field exists everywhere. What we call a particle is a localized excitation, a small concentration of activity within that field. This means that matter is not something added to space, it is something that emerges from it. Space, through its fields, gives rise to matter. This realization transforms the meaning of empty space. Even in regions where no particles are present, fields still exist. These fields can fluctuate, carry energy, and influence motion. Space is not a passive backdrop but an active participant in physical processes. Feynman often stressed that when physics describes nothing, it rarely means true nothingness. What appears empty may still be rich with structure and potential through fields. Fields also redefine how reality evolves. Changes do not occur abruptly or mysteriously. They propagate through fields, linking cause and effect across space and time. When something happens at one location, its influence spreads through the surrounding field, shaping future events elsewhere. This makes reality continuous and connected. Every point in space is part of an ongoing conversation governed by field dynamics. Another profound implication is that space itself acquires physical properties. Because fields can store energy and momentum, space can be energized. Because fields can change and propagate, space can be dynamic. In modern physics, even the geometry of space and time behaves like a field, capable of stretching, bending, and vibrating. Matter tells fields how to behave, and fields tell matter how to move. This mutual relationship dissolves the old boundary between object and environment. Feynman emphasized that this view replaces mechanical pictures with deeper understanding. The universe is not a machine made of parts pushing and pulling each other. It is a continuous system where patterns in fields give rise to everything we observe. Stability, motion, and structure emerge from the way fields organize themselves. Atoms, molecules, stars, and galaxies are all stable patterns in fields, not isolated things assembled piece by piece. This perspective also changes how we think about existence itself. Reality is not defined solely by what can be directly observed. Fields may be invisible, but their effects are real and measurable. They determine how matter behaves, how light travels, and how energy flows. Accepting fields as real expands our notion of what it means for something to exist. Existence is not limited to tangible objects, it includes the underlying structures that make those objects possible. Fields also unify the laws of physics across scales. The same fundamental principles apply whether describing subatomic particles or cosmic structures. This unity suggests that reality is governed by a small set of deep ideas rather than a collection of unrelated rules. Fields provide the common language that makes this unity visible. Feynman believed that understanding fields is not just about learning physics, it is about learning how to think correctly about nature. Fields encourage us to focus on relationships, structures, and processes rather than isolated objects. They teach us that what matters is not just what exists, but how it exists and how it interacts with everything else. In this final keynote, fields emerge as more than scientific tools. They are the framework through which reality expresses itself. Matter, space, and motion are not separate chapters of nature's story. They are different expressions of the same underlying field-based structure. By connecting matter, space, and reality itself, the concept of fields offers one of the most profound insights physics has ever achieved. It reveals a universe that is unified, dynamic, and deeply interconnected at every point. This is the vision Richard Feynman sought to share, a view of nature where nothing stands alone, and everything is woven together through the invisible, yet fundamental, presence of fields.